Okay, so this is for chapter 2, measurement and problem solving. Uncertainty in measured number is indicated by the last reported digit. Some numbers are exact. There's no uncertainty for those numbers. Measured numbers are not exact, have uncertainties. The uncertainty is indicated by the last reported digit. Example, measuring global temperatures. Average global temperature have risen by 0.6 degrees Celsius in the last century. By reporting a temperature increase of 0.6 degrees Celsius, the scientist means 0.6 plus minus 0.1 degrees Celsius, which means the real global temperature increases is somewhere between 0.6 plus 1 becomes 0.7, or 0.6 minus 1, 0.1 becomes 0.5. The degree of certainty in this particular measurement is critical, influencing political decisions that directly affecting people's lives. Reporting measured scientific numbers. So in this example, we have 5 digits, and the first 4 digits in blue, they are certain. The last digit in red is estimated, so therefore it's uncertain. The first 4 digits are certain, the last digit is estimated. The greater the precision of the measurement, the greater the number of significant figures. Scientific notation has 2 parts. This is one example of scientific notation. The first is the decimal part, 1.2. Exponential part is 10 to the negative 10 in this example. And this negative 10 is called the exponent, sometimes called exponent n. The number written in scientific notation has 2 parts. A decimal part, a number that is between 1 and 10. An exponential part, 10 raised to an exponent n. Writing very large and very small numbers. A positive exponent means 1 multiplied by 10 to the nth, 10 n times. For example, 10 to the 0. That's a special case. So any non-zero number raised to the power 0 is 1. 10 to the positive 1, which means 10 times 1 times. And 10 to the positive 2, which means multiply 10 twice. So 10 times 10 equals 100. And 10 to the positive 3. So we'll take 1 multiplied by 10 3 times. It becomes 1,000. A negative exponent negative n means 1 divided by 10 n times. For example, 10 to the negative 1 is equal to 1 divided by 10, becomes 0.1. 10 to the negative 2 means 1 divided by 10 twice, or 2 times. So 1 divided by 10, then divided by 10, it becomes 0.01. Similarly, 10 to the negative 3 equivalent to 1 divided by 10 3 times. So 1 divided by 10, then divided by 10, then divided by 10 again, it becomes 0.001. To converting a number to scientific notation, find the decimal part, find the exponent. Move the decimal point to obtain a number between 1 and 10. Multiply the number, the decimal part by 10 raised to the power that reflecting the movement of the decimal point. So in this example, we locate the decimal point, initially the decimal point behind this 3. We move like 3 times to somewhere between 5 and 9. So therefore, we have a scientific notation become 5.983 times 10 to the 3. So this 3, that's exponent 3 comes from, we move the decimal point 3 times until we get a 5.983. And we move to the left. So if we have a number, we move the decimal point and we get a number between 1 and 10. In this example, we move the decimal point to the right 4 times, we get 3.4. Before we move to the right 4 times, therefore the exponential part is 10 to the negative 4. If the decimal point is moved to the left, the exponent is positive. If the decimal point is moved to the right, the exponent is negative. Express each sample in scientific notation, and there are 4 numbers. And you can stop the video and do a practice and check the answer. The solution is we are going to locating the decimal point. The first number is here, and so on. Then we begin to move the decimal point for those 4 numbers are moved to the left. And here we get a number between 1 and 10. So the first we move like 9 times, so we get a 7.376, and then this 9 is indicated here. We move to the left, so positive 9. For B, we also move 9 times, so therefore we have 10 to the positive 9 and 1.404 times 10 to the positive 9. For the C, we will move 7 times to the left, so therefore we get 1.1258 times 10 to the positive 7. For D, we move 6 times to get 4.677, therefore we have 10 to the positive 6. Now these 4 numbers, they are all smaller than 1, so therefore we have to move the decimal point to the right. Then you can pause the video and check the answer. So the answer for the first number is 1 times 10 to the negative 9. For the second number will be 1.4 times 10 to the negative 1. For C, it's 1 times 10 to the negative 12. And then for D is 1 times 10 to the negative 6. Estimating 1 more digit beyond the smallest marking. So in this example, we can see we want to measure the mass of these nuts. And the balance has the smallest marking every 1 gram. So we have this 0 gram, 10 gram, and we have those marking, 10 marking between 0 and 10. So therefore we know each marking is 1. We estimate to the 10th place. So that's how we measure correctly using the instrument. To estimate between marking, mentally divide the space into 10 equal spaces and estimate the last digit. So this reading for this line here is between the marking 1 and 2. The first marking is 0, this marking is 1, this marking is 2. So therefore, we cannot stop just simply say 1. We have to make 1 more estimate, get 1 more digit. So therefore, our reading for this mass is 1.2 gram. And this 1.2, this last digit from mass estimate, so therefore different people will have different estimate. Some people might estimate 1.2, and some people might estimate 1.3. That is all allowed. Estimating 100 place of a gram. In this example, we have a different balance. The balance has a marking every 10th of a gram. You can see we want to reading the marking here. This is 1 gram, this is 2 grams. So therefore, between 1 and 2, there are 10 small spaces. So therefore, we have the smallest marking 0.1 gram or the 10th gram. So therefore, we can estimate the 100th gram. And we know this mass from this marking, we can see clearly either between 1.2, this one 1.2, and 1.3. So I have marked this. The first marking here is 1.2. The next marking here is 1.3, 1.3, and 1.2. So you don't stop for just simply say 1.2, neither 1.3. So you do your estimate 1.26. Similar for this graduate cylinder, so at right has a marking every 0.1 milliliter, reporting the volume for this liquid, and you want to estimate between the markings. We can see this is 4.5. This marking here is 4.5. And so again, this is 4.5. So then this marking here is 4.6. So 4.5, 4.6. So this meniscus, the lowest point is the line you want to read. So therefore, you don't stop at 4.5, neither 4.6. You want to estimate. So therefore, one possible reading, the textbook given is 4.57. And if you're reading 4.58 or 4.56 is all acceptable. But you don't read like a 4.63 because this meniscus clearly is below 4.6. Similarly to this practice, so this is reading this thermometer, and your two marking that is very close to what you want to read is this 2 line, and this 100. So this the 103, and this is the 104. So therefore, your reading should not stop at 103, neither 104. And the correct reading should be estimate only one more digit. So therefore, the answer is B. Counting significant figure for measured numbers. First rule, so those are the rules you want to follow to counting how many significant figure in a measured number. 1. All non-zero digits are significant. We know we have the decimal system. Non-zero digits are 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 0 digit is just 0. So we use decimal system. So when you have a number, any of those non-zero digits are always significant. In this example, 1.5, if I tell you 1.5 is a measured number, and there are 2 digits, and both digits are non-zero. Therefore, we say this 1.5 has 2 significant figures. Interior 0. So this digit can have at different place. Interior 0 means in between 2 non-zero digits. So in this number 1.05, this 1 digit is non-zero. This 5 is non-zero. So this 0 here is the interior between 2 non-zero digits. So therefore, you counting this as significant. So therefore, altogether, 3 significant figures. Leading zeros are not significant. What is leading zero? Leading zero is before the first non-zero digit. So in this example, this first 3 zeros, these are leading zeros. Okay? So these are the leading zeros. You don't count them as significant. So therefore, this number still has 3 significant figures. To clearly show that, or another way to show that, you can write this number in scientific notation. You can write 1.05 times 10 to the negative 3. So this is scientific notation. When you count in significant figures for a scientific notation number, you don't worry about the exponent part, just see the decimal part. This decimal part clearly is 1.05, has 3 significant figures. The trailing zeros may or may not be significant. Trailing zeros are significant if the decimal point is written. So in this example, we have this 0 is trailing 0. Okay? So this 0 here is our trailing 0. This number has the decimal point written here. Therefore, this 0, the trailing 0, is significant. And altogether, within 1.05 has 3 significant figures, then plus 0, we have 4 significant figures. So then similarly, this 150.0, and this 0 is also the trailing zeros. Both these 2 zeros are trailing zeros. But this number has the decimal point written, so therefore we will counting both of them as significant. Therefore, we see this has 4 significance. Now, 0 at the end of a number without a written decimal point are ambiguous, should be avoided by using scientific notation. For example, if you simply write 150, it's called ambiguous. But if you know 150 has 2 single figures, then you should write that as 1.5 times 10 to the 42. And if you know 150 has 3 single figures, then you will write 1.50 times 10 to the 42. And the other type of number is the exact number. So how do you know the number is exact? Well, exact numbers has, first of all, exact number has unlimited number of single figures. Exact number come from a counting of a discrete object. So for example, counting how many people in our class. And another way to get to see the number are exact numbers. Exact number are integer numbers that are part of an equation. And let me give you one example of this. We know let's see the area of a triangle equals half times the base, and use b for base, and height. So that in this is the formula or equation. So in this equation, you have 2 numbers, the 1 and 2. And obviously, you also need to know what is the base, what is the height to calculating the area of triangle. But if this one or 2 just come from the equation for the area of triangle. So no matter what triangle do you have, when you calculating the area of triangle, you always have to use 1 divided by 2. So this 1 and 2 are the exact number, which means even though they look like only have 1 digit, but you see they have unlimited number of single figures. And then another way to see another source or another place to give you the exact number are most of the definition quantities. So what is the definition? Example of definition, let's see, 1 meter equals 100 centimeters. Okay? So this is definition. And then in this definition, we have 2 numbers. We have 1 and 100. So then most of the definition, the number in most of the definition are exact numbers. Again, they looks like only 1 digit, or this 100 looks like ambiguous. But if they come from definition, they have unlimited number of significant figures. And so another place will give you the exact number, some conversion factor from defined quantities, and so therefore they are also exact numbers. But some are not. One conversion is 1 inch equals 2.54 centimeters. So this is exact conversion, but it means this 1 is exact, 2.54 is also exact. Right. So for this practice, again, close the video, stop the video, and practice, then come back to the answer. So how many significant figures are in each numbers? And so you first identify those numbers are measured or exact. If they are measured, you are using the 4 rules. If they are exact, you know, they have unlimited significant figures. Okay, so the first one, this 0.0035, there are 3 zeros. These 3 zeros are the leading zeros. They are not significant. Therefore, this has only 2 significance. And then this 1.080. So this 0 is at the end of a number, but the number has a decimal point. So therefore, this 0 counting as a significant. This 0 is the interior 0. So therefore, we have 4 significants. And this number just has 4 non-zero digits, 4 significants. This is scientific notation. So this part does not matter. 209 tells us it has 2 significants, so therefore 2 significants. 1,000 is equal to 12. So there are two numbers. The one number is 1, the other number is 12. Because this is the definition, so therefore it has unlimited significant figure for both for 1 and also 12 in this equation. And then we have this 100.00. So we have this decimal point written here. So therefore this 40 at the end of this number, they are all significant. So altogether we have 5 significant figures. And then this 100,000 as written, it is ambiguous because we don't have a decimal point. 8 does not have a decimal point written. So therefore we see it's ambiguous. But if you know somehow this number has how many sig fig, then you can use scientific notation. Okay. So once you know how to show how many significant figures, sometimes you need to do the rounding. And our user will do the rounding. When number are used in calculation, the result is rounded to reflecting the significant figures of the data. For calculation involving multiple steps, round only the final answer, do not rounding off between steps. This practice prevents a small rounding error from affecting the final answer. Use only the last or leftmost digit began dropping to decide in which direction to round. It means rounding up or rounding down. Ignore all the digits to the right of that. Rounding down if the last digit drop is 4 or less. Rounding up if the last digit drop is 5 or more. Then how do we decide how many significant figures to keep when we want to do the rounding? Then we will see those rules to tell us how many significant figures so we keep when we do the calculations. The first type of calculation is multiplication and division. When you multiply or dividing numbers, the result has the same number of significant figure as the number with the lowest amount of significant figure. So let's see some examples. We have these three numbers multiply, and we use calculator to get 45.0118. So we identify in all these three numbers are used to multiply to get this 45.0118. The first number is 5.02. It has a 3 sig fig. The second number has a 5 sig fig. Last number has 2 sig fig. So then we compare this 3, 5, and 2. So 2 is the lowest. That means our answer sure has only 2 sig figs. Now we know how to do the rounding. So we're counting 1 sig fig, 2 sig fig. Looking to the right is 0. So 0 is less than 5. So therefore, we simply rounding down, we get 45. Another example is we have this 5.892 divided by 6.10. We get this number 0.96590 from calculator. So then what will be our final answer? So we're counting again how many sig figs in these two numbers. So this 4 sig fig, and this has 3 sig fig. And we compare this 4 with 3, so 3 is lower. So therefore, we will keep a 3 sig fig in this number. We know this 0 is the leading 0, does not count as significant. So therefore, 1 significant figure, 2, 3. So we're going to round off every digit to the right of this 5. We look into the right digit of this 5, we see 9 is rounding up. So therefore, we get 0.966. When you do addition subtraction with significant figures, the result has the same amount of decimal place as the number with the lowest amount of decimal place. Okay, so here we have 3 numbers adding. and we count how many decimal places. So the first number has 3 decimal places. You know decimal place, that means those are digits after the decimal point. So 1 decimal place, 2 decimal place, 3 decimal place. 1 decimal place, 2 decimal place. 1, 2, 3, 4. So that's what we get. So this has 3 decimal places, and this has 2 decimal places, and this last number has 4 decimal places. So put this number in the calculator, we get 5.4125. So shall we keep all the 5.4125, or shall we run it somewhere? We compare those decimal places. We compare 3 to 4. So 2 is the lowest. Okay, so 2 is the lowest decimal place. Therefore, we will keep 2 decimal places for our answer, and so therefore our final answer will be 5.41, because we look into the right, we have 2, we simply drop down. And this line just tell you another way to see how you cutting, how you running off, by draw the line that is right next to the number has lowest number of decimal places. Okay, so another example, we have 2 numbers subtracting, whether they are subtracting or adding, or even have a mix of these 2 operations, adding some number and subtracting some number. Just counting how many decimal places for each number. So 5.9 has 1 decimal place, 5.221 has 3 decimal places, and then our answer should have 1 decimal place, because 1 is low. So you want to keep this. So when you keep this, will give you a number has 1 decimal place. You look to the right is 7, so you're running up 5.7 is our answer. It has 1 decimal place. All right. So the basic unit of measurement, the unit system for science measurement based on the metric system, you call the International System of Units. The front word, System International. And this table shows you there are 4 basic quantities: length, mass, time, temperature. And in SI, the base unit for length is meter, for mass is kilogram, for time is second, temperature should be Kelvin. And sometimes the number is very big or very small, so we conveniently use prefix. So we commonly know those giga, mega, and then we also know some of the common like deci, centi, milli. Just get familiar with this table. So here are the prefix, and here are the simple. Most times just use simple, and then the meaning, and then those numerical equivalency. So we saw one example we said before is my screen sound become large. I said 1 meter equals 100 centimeter. So this prefix, this here centi. So you're choosing a prefix multipliers, choosing the prefix multiplier that is the most convenient for a particular measurement. Pick a unit similar in size to the quantity you are measuring. A short chemical bond, for example, is about this much meter. Which prefix multiplier should you use? Well, you can see this kind of between 2 prefix. A small prefix is pico 10 to the negative 12. A larger is nano 10 to the negative 9. So therefore, you can choose actually the one probably closer will be the even one. Most of the scientists use pico. The most convenient one is probably the picometer, chemical bond measuring about 120 picometers. So the volume is a derived unit, because we see in that table we don't have a volume. A derived unit is formed from other units. So that's what I mean by a derived. Many units of volume, measure of space, are derived units. Any unit of length, when cubed, raised to the third power, become a unit of volume. For example, cubic meter, cubic centimeter, cubic millimeter are all units of volume. So you can see this centimeter, millimeter, and meter, obviously they are different, but when something common, if they all raised to the third power, all have this exponent 3. Getting to an equation to solving from problem statement require critical thinking. So therefore, one way to solve the problem or problem solving is using unit conversions. No simple formula apply to every problem, yet you can learn problem solving strategy and begin to develop some chemical intuition. So one way I will say here is the unit conversions. Unit conversion type. Many of the problems can be thought of as unit conversion problem in which you are given one or more quantity and asked to converting them into a different units. Specific equation type. So other problem require the unit of specific equation to get to the information you are trying to find. Units, using the super unit conversion is also have another name, is using dimensional analysis to converting between units. Units are multiplied, divided, and cancelled like any other algebraic quantities. Using unit as a guide to solving problem is called dimensional analysis. Always write every number as with its associated unit. Always include the units in your calculations, dividing them and multiply them as if they were algebraic quantities. Do not let a unit appear or disappear in your calculation. Unit must follow logically from beginning to end. For most conversion problems, we are given a quantity in some unit and asked to convert the quantity to another unit. This calculation takes this form. The information given multiplied by the conversion factor or conversion factors equal to the information solved. So writing another way is the given unit multiplied by conversion factor. Conversion factor means conversion fraction. And then you will cancel out the given units, you get the desired unit. So converting between units, conversion factors are constructed from any two quantities known to be equivalent. For example, 1 inch equal to 2.54 centimeters. So this is an equivalent. We can construct the conversion factor by dividing both sides of the quantity or the equality by 1 inch and cancel the units and the number. So therefore, 1 cancel with 1 still 1. So what we get is really 2.54 centimeter over 1 inch equal to 1. The quantity is equal to 1 can be used to convert between inch and centimeters. So because this fraction is 1, that means you can multiply 1 on any number to get the same number. So that's the reason you can use conversion fraction. Converting between units, conversion factor can be inverted because they are equal to 1, and the inverse is also 1. Therefore, when we have a 2.54 centimeter over 1 inch equal to 1, we can also write 1 inch over 2.54 centimeters. So which of these fraction you use depend on the given quantity. In solving problems, always checking if the final units are correct and consider whether or not the magnitude of the answer makes sense. For example, if you want to convert from centimeter to inch, you are going to use this fraction. So in this fraction, for this given problem, 44.7 centimeters, the centimeter is on in the numerator. In this fraction, the centimeter in the opposite place in the denominator. So therefore, when we multiply, they cancel out, and you will have the inch, which is the unit we want. So usually you will have a solution map. A solution map is a visible outline that shows the strategic route required to solve a problem. For unit conversion, the solution map focuses on units and how to converting from one unit to another. The solution map for converting from inch to centimeter is as follows, even though it's very simple, as you saw already know how to use the conversion fractions. You simply see I starting from inch, I want to convert into centimeter. And then you decide I will use this fraction. So this just a generic map, and depending on the question, if the question give you centimeter, you will reverse the process and also reverse the fraction. The solution map for converting from centimeter to inch is as follows. So that we said, if the question give you centimeter and you want to convert into inch, so then you just reverse the direction and also reverse the conversion fraction. The general problem solving strategy identify the starting point, the given information, identify the end point, what you must find, devise a way to get from the starting point to the end point using what is given as well as what you already know or can look up. You can use a solution map to diagram the steps required to get from the starting point to the end point. In graphical form, we can represent this process as given, then with solution map, details depend on the problem, then to find. So each step in the solution map should have a conversion factor with a unit of the previous step in the denominator and unit of the following step in the numerator. So I'll see what I mean by this example. How many feet in 194 centimeters? Our solution map will be from centimeter to inch and then from inch to feet. So this is one example of the solution map. Just obviously this solution map just depends on what you know. So we assuming we know how to convert from centimeter to inch, then we know how to convert from inch to feet. But if you know there's an equation between centimeter and feet, then you can skip this, or you can combine the two steps in one step. So this is a two-step problem. We will use our first step to converting from the centimeter to inch. Then the second step, the second fraction will convert the inch to feet. So we will keep this map here, and let's say we have one quantity we want to convert in 194 centimeter. We multiply by the two fractions put it here. So what that means on the last slide is each fraction will have the unit from the previous previous step in the denominator, so therefore they can cancel out. And then finally, you will see there's only one unit, that is the unit we want. So after you cancel out units, just take those numbers, put in your calculator, do the dividing or multiply to get this number. And obviously, this is not a final answer yet. You get this number from the calculator, then you decide where should rounding, depend on what calculation we did. For this example, we did the calculation in multiply and divide. We counted how many sig figs. So this has a 3. This all the number here are exact. So therefore, we want to keep a 3 sig fig. So all the number here, they are exact numbers. Exact number has unlimited number of significant figures, but this number has 3 significant figures. So compare 3 with unlimited, obviously less. So therefore, your answer for the 6.36. And similar for this conversion, so you are given 30 milliliter, you want to convert into parts. And so the question also gives you these two equations. So your solution map will be something like you want starting with what is given. What is given is the milliliter. So it gives you 30.0 milliliter. So then you see, how can I get what we want? What we want is the parts. Probably using both equations. So we're first converting the milliliter to liter. And then once we get liter, then we convert the liter to the parts. So therefore, we are going to use two fractions. And the first fraction, so as one slide tell you, you want to put the quantity that is from the previous step in the denominator. Typically, that's true. So now we're starting with milliliter, so therefore we are going to put this milliliter in the denominator, and then the other unit. So this one will be in the numerator, and this one will be in the denominator. So once we get that, we know we can cancel out the milliliter with the milliliter. Then we will get the liter. So in this step, so liter will be from the previous step. Therefore, we'll put it in the denominator, and then we will put the QT, the parts, in the numerator. Then the number just comes from the equation. So one comes from this one here. Then what number for the part? Well, this number here, 1.057, 1.057. Right. So that's our map. And then we'll just apply our map. And we have these two fractions. And we can see the cancellation. And this one is given. And then this is what we find. Again, you have to decide the sig fix. So this one has 3 sig fix, and this one has 4 sig fix. And all those numbers here are exact. So therefore, our fewest sig fix is 3. And then we decide these two are not significant. Therefore, 1 sig fix, 2 sig fix, 3 sig fix, and our final answer is 0.0317. What the unit? What is part? So sometimes you convert a unit raised to a power, like cubic meter, cubic centimeter, or square feet. When converting quantity with unit raised to a power, the conversion factor must also be raised to that power. We cubic both sides to obtain the proper conversion fraction. That's one example. So we know 1 inch is 2.54 centimeter. But when you want to convert in between cubic inch and cubic centimeter, you have to cubic the unit and also cubic the number. So therefore, we get this 254 cubic centimeter cubic equals 1 cubic inch cubic. And it turned out to be this number. We do the same things for in the fractional form. So for example, here you want to convert in 1255 centimeter cubic to inch cubic. So we will use this last equation to make a conversion fraction to cancel out this cm cubic, get inch cubic. Okay, don't forget, you must cubic this 2.54 and inch to get this type of unit raised to a power. So this example is converting liter to cubic inch. And we usually go through a few steps of solving problem. The first step is sorting, which means identify what is given and what you want to find. So we given 5.70 liter, we want to find out how many inch cubic. Then we see our strategy, which pretty much you want to get a conceptual plan or solution map. So what do we say we are going to go from liter to milliliter? And then we know the equation between liter and milliliter is written like can be written as 1 milliliter equals 0.001 liter. So therefore, from that we get this equation, and then from the milliliter we can get to centimeter cubic, and that's simple. So 1 milliliter equal to 1 centimeter cubic. Then we can convert it from centimeter cubic to inch cubic that what we did in last slide. So again, here you will see the 1 get cubed, then the 2.54 also get cubed. Don't forget that to get the inch cube and cm cube. Okay, so once we have this three fractions, then we are ready to apply them. We're starting by the given 5.70 liter. Then we multiply by the first fraction, and we can see the cancellation of the liter. And then we multiply by the second fraction, then we can see the cancellation of the milliliter. Then we multiply by the last fraction, we see the cancellation of the centimeter cubic. So now we just take those numbers, multiply and divide. We have this number, then we keep the smallest significant figure, which will come from this number, which gives us 366. So therefore, we have 348. Another very important physical property is density. Why do some people pay more than 3,000 for a bicycle made of titanium? Because titanium has a very small density, so your bicycle is very light, easy to use. We describe this property by seeing that titanium density is 4.50 grams per centimeter cubic. Compare with the Rn, almost like twice of that heavy. Density of a substance is the ratio of its mass to its volume. So we see equation for density is density equal to mass over volume, or D equal to M over weight. So we calculating density. We calculate the density of a substance by dividing the mass of a given amount of the substance by its volume. For example, if a sample of liquid has a volume of 22.5 milliliter and a mass of 27.2 grams, to find the density, we use the equation D equals M over weight. So M is the mass with volume, and the given problem mass is 27.2 grams, volume is 22.5 milliliters. Therefore, we divide, we keep the unit, and we get 1.21 gram per milliliter. You can use density as a conversion factor. We can use the density of a substance as a conversion factor between the mass of the substance and its volume. Here's one example. Find the liquid substance with density of 1.32 grams per centimeter. What volume should be measured to deliver a mass of 68.4 grams? So our strategy or our process of solving the problem is sorting. So we identify what is given, what we want to find out. Then we have this solution map. Our solution map will be like this. So we were starting the given with like the given gram, and then we use the other given quantity, which is density, make the conversion fraction, and then we converting from the centimeter cubic to milliliters. But so therefore, we try, we write up our given mass, 68.4 grams, multiplied by this fraction. Again, this fraction is from the, so this fraction is from the given density. Given density here. So we then can see the cancellation of the unit correctly, we get the milliliter. Therefore, if you measure for that given substance, whatever that is, It has density 1.32 gram per centimeter cubic. If you measure 51.8 milliliter, you will get 68.4 grams. So this is the learning objectives for this chapter. When you review, go by each objective, see if you can understand, and see if you can do some of the program. Okay, so this is the end of this chapter 2.